Welcome to Spring LIB.
Okay, so we're doing chapter 35, problem 45 here. So we have monochromatic light, which is these red lines, and they're incoming falling on a transmission diffraction grating at an angle phi. So each of these are all entering at an angle phi, because they're all parallel here. And we want to show that equation 13 for diffraction maximum must be replaced by this equation here, d sine phi plus sine theta, and this equals plus or minus n lambda for positive m's. Okay, so let's start doing some geometry here. So let's look at this first path. We have this first top red path coming in, hitting it at an angle with respect to the horizontal of phi, and transmitting off with respect to an angle of theta. So we want to figure out the differential path lengths here. So this one is also going to come off at some angle out here, such that this angle is also theta. So let's figure out how much extra path was traveled. So if we extend this rectangle out, we should see that I'm going to mark this in blue here. So this section and this section are extra path that is traveled than the next line. So we want to figure out, if we're trying to find the path length gain, is going to be this distance here, which we're going to call delta L2, and this distance up here, which we call delta L1. Okay, so now let's figure out how to find these. Well, if we look at this triangle, this is delta L1. So if we look at the triangle made so I'm just trying to figure out this triangle we want to draw. So it's this triangle right here, who has an angle phi here. So what this tells us is that delta L2 is given by d sine phi, and we can do the same thing over here with this triangle. So we have one triangle there, one triangle here. And from that, we can see that delta L1 is given by d sine theta. Okay, so if passing through the grating at the higher ray travels an extra distance, delta L1 plus delta L2, which we're going to define as delta L. So each ray above travels an extra distance, delta L, from the ray below it. So the total path length difference, we just set this equal to an integer times the wavelength. And we're going to add a plus or minus, and this is the same as what we just added, d sine phi plus d sine theta. Let me rewrite that. So this is exactly what we wanted to show. Equals n lambda, plus or minus. Okay. So let's go back and do that again. So this right here, oops, let me draw this in green. So this right here is phi, and this along here is d. This here is theta. So we can find this value and this value, respectively, by using the signs. So that's what we did, and we set that equal to integer times the wavelengths to get the interference pattern how we like. Okay, so moving on to part B, it says, what's up with this plus or minus sign, right? So the plus or minus sign just allows for the incident angle and the diffracted angle to have either positive or negative values. Or you can also think of it as positive or negative integers, right, on either side of coming in. So that's all that is allows positive or negative theta / phi. Cool. And lastly, part C says green light with a wavelength of 550 nanometers is incident at an angle of 15 degrees to the normal on the diffraction grating, and it says 5,000 lines per centimeter. Lines per centimeter. So we want to set find the first angles at which the first maximum occur. Okay, well, we know that sine theta is in lambda over d. So theta is the inverse sine of in lambda over d. And we said the first maximum, so let's take the inverse sine here of okay. So this is for the normal diffraction grating, right? But we just figured out that we needed to replace it with this. So I'm actually going to erase what I have here, or at least try to erase that. Okay, so now we have d sine phi plus d sine theta equals n lambda, plus or minus n lambda. Okay, so from this, we can figure out sine theta is negative sine phi plus or minus m lambda over d. Cancel all that guy out. Okay, so now we can take the inverse sine, and we get theta. What we want to figure out is the inverse sine of negative sine phi, and we're using positive 1 for our plus or minus 1, m equals 1. So this is just lambda over d. So let's plug this in. So now we have inverse sine of negative sine of 15 degrees plus or minus 400, oops, not 400, this is 550 nanometers over, what's our d? Well, that is 0.01 meters divided by 5,000 lines. Okay, so if we plug this into our calculator for both plus and minus, we get thetas of 0.93 degrees and negative 32 degrees. Awesome.